Have you ever wondered why a diamond is so unbelievably hard while the graphite in your pencil is so soft? I mean, they're both just rocks, right? Or why some stones are worth millions while others are just, well, stones. Welcome to today's explainer. We are going deep, literally, into the Earth's crust to uncover the fascinating chemical secrets of minerals, and we'll explore how these natural treasures are powering a trillion-dollar industry.
By the end of our journey today, you won't just know the answers to those questions, you'll actually be able to visualize the chemistry behind them. You're going to understand why precise atomic arrangements, like the ones that make a diamond unbreakable or pencil lead just flake away, are quite literally shaping modern global economies.
Here is our roadmap for today. We'll start with the building blocks, move on to identifying minerals like a pro, explore the mineral family tree, talk about bringing it to the surface, and finally, look at KSA as the new mining frontier.
All right, let's dive right into Section 1, the building blocks.
First things first, let's get our definitions straight, because people use mineral and rock interchangeably all the time, and they're actually very different. A mineral is a solid, inorganic material with a highly specific chemical composition and a unique crystalline structure. Think of a mineral like a specific type of Lego brick. A rock, on the other hand, is just a solid collection of one or more of these minerals pushed together. So the rock is the castle you build out of those individual Lego bricks.
So, what are those individual Lego bricks actually made of? Elements. And get this, just 8 elements make up a staggering 98.6% of the Earth's entire crust. The most common ones by far are oxygen and silicon. The basic unit of these elements is, of course, the atom, with its positive nucleus and a cloud of negative electrons. To put the sheer scale of this into perspective, a single copper penny contains about 1.56 times 10 to the 22nd power of copper atoms. That is a mind-boggling number. Now, how do these atoms actually stick together to form minerals? Well, they bond in a few distinct ways. First up, we've got ionic bonds, where atoms actually swap electrons with each other. Halite, which is just your standard table salt, is a perfect example of this. Then you have covalent bonds. Here atoms share electrons to fill their outer shells, and this creates an incredibly tight grip. This is the absolute strongest type of chemical bond and is exactly why a diamond is so unbelievably tough.
We also have metallic bonds. This is where electrons just kind of flow freely in this sea around the atoms, and that's what gives metals their high density and that characteristic shine. Finally, we have van der Waals forces, which are incredibly weak electrical ties. And hey, this actually answers our earlier question. You see, graphite is made of carbon, exactly like a diamond is, but its layers are held together by these super weak forces. That allows the layers to just flake off easily onto your paper whenever you write.
Moving right along to Section 2, identifying minerals like a pro.
Out in the field, geologists don't always have fancy lab gear, so they rely on visual and physical tests. First is luster, which is simply how light reflects off the mineral's surface. It might be distinctly metallic like galena or non-metallic and earthy like orthoclase. But since outward color can be super deceiving because of random impurities, experts use the streak test. This reveals the color of a mineral when it's crushed into a powder. For instance, the metallic mineral hematite might look gray, but it will always leave a distinct red streak on a test plate.
To test hardness, geologists use the famous Mohs scale. This ranges from 1 for extremely soft minerals like talc, all the way up to 10 for diamond. And the coolest part is you can actually test this at home. A standard copper penny has a hardness of about 3.5, and a glass window is about 5.5. By seeing what object scratches what, you can very quickly narrow down exactly what kind of mineral you're looking at. It's like a real-world puzzle.
And geology is surprisingly hands-on. Some minerals practically identify themselves with what geologists call distinctive properties. They're almost like special superpowers. If you have a piece of magnetite, it will literally pull a magnet right out of your hand. If you drop a tiny bit of hydrochloric acid on calcite, it'll immediately start to bubble and fizz. And halite, well, as we learned earlier, halite is just rock salt. If you give it a quick lick, it tastes exactly like you'd expect. Though, for sure, please make certain you know it's halite before you go around tasting random rocks in the wild.
Okay, let's look at how all these are organized in Section 3, the mineral family tree.
When we categorize all these minerals based on their negative ions, which are known as anions, we immediately see an incredibly lopsided family tree. An overwhelming 95% of the Earth's entire crust belongs to just one single family, the silicates. Everything else, all the gold, the silver, the salts, the carbonates, they all have to squeeze into that tiny remaining 5% slice of the pie called non-silicates.
So, what is the secret to this massive dominance of silicates? It all comes down to the silicate tetrahedron. It's this incredibly stable little pyramid shape that consists of exactly one silicon atom in the center, surrounded super tightly by 4 oxygen atoms at the corners. Because oxygen and silicon are so abundant on Earth, these tetrahedrons form everywhere, linking together in chains, sheets, and 3D frameworks to create common minerals like quartz and feldspar.
But what about that remaining 5%? Well, the non-silicates include native elements, which are pure, uncombined elements like pure gold or silver. You also have oxides, sulfides, carbonates like calcite, and sulfates like gypsum, which, by the way, is exactly what the plaster in your home's walls is made from. Even though they are rare compared to silicates, this tiny 5% group is actually where we find some of our most economically valuable ores.
So how do we actually get this stuff out of the ground? That brings us to Section 4, bringing it to the surface.
The extraction method entirely depends on depth. For near-surface blocks of rock, like marble or granite, you use quarrying. You simply dig an open pit and carefully cut the blocks out. If the minerals are shallow but spread out, open-pit mining removes the surface layer in angled, terrace steps to keep the miners safe. But for extremely deep deposits like iron ore or coal, engineers have to build shaft mines. They drop massive vertical tunnels and use lifts to reach those deep underground chambers.
Once you're deep underground, the engineering techniques get absolutely wild. Take a method called shrinkage stopping. Miners excavate a vertical vein of ore, but they intentionally leave the broken ore right there in the chamber. Why? Because it acts as a rising floor. The workers literally stand on the rubble they just blasted so they can reach the ceiling and drill the next horizontal slice upwards. It's just a brilliant, dynamic way to safely extract minerals from steeply inclined deposits.
Now, let's zoom all the way out to the macroeconomic scale in Section 5, KSA, the new mining frontier.
Let's talk big business. In a massive 2024 update at the Future Minerals Forum in Riyadh, Saudi Arabia announced that its estimated mineral wealth now sits at an astounding $2.5 trillion. That is a staggering 90% increase from previous years. The Arabian Shield holds 48 different types of minerals, boasting massive new discoveries of rare earth elements, gold, copper, and huge increases in phosphate. Mining is now officially the third pillar of the Saudi national economy.
While these trillion-dollar numbers are definitely making headlines today, this isn't just an overnight success story. This journey actually began way back in 1931, when King Abdulaziz directed the first modern mineral explorations. By 1939, the Ma'ad al-Dahab mine, which is still the oldest operating mine in the country, was already extracting massive amounts of ore, yielding over 900,000 tons in just its first 15 years. This steady, decades-long progression paved the way for the foundation of Ma'aden in 1997, which is driving so much of this modern expansion.
Now, to manage this staggering $2.5 trillion of wealth, the kingdom operates under a very clear legal framework. According to Article 2 of their mining law, all mineral deposits are strictly state property. This applies to all ores, all forms, and all compositions. So whether it's sitting right on the surface, buried a mile underground in a shaft mine, or even within marine territories, the law ensures that these vast natural resources are structurally bound to benefit the state and the national economy as a whole.
And that, incredibly, brings our journey full circle. From the super-tight sharing of electrons in a microscopic covalent bond, to a geologist scraping a rock on a plate, to engineers blasting vertical shafts deep into the earth, all the way up to a $2.5 trillion national economy in the Arabian Shield. Minerals truly are the physical and economic foundation of our modern world. Understanding them isn't just about knowing your rocks. It's about understanding the very building blocks of human civilization. If you enjoyed this explainer and learned something new, make sure to hit that like button and subscribe for more deep dives.
I really hope this explainer gave you a brand new perspective on the ground beneath your feet. But before you go, I have a fun question for you to ponder. Based on everything we learned today about rarity, utility, and value, if you could own a mine of any specific mineral on Earth, which one would it be and why? Let us know down in the comments. Thank you so much for joining me today. Keep learning, and I'll see you in the next one.